There is a solar system on a wall somewhere near you, a classroom poster, a placemat, the page at the back of a school book, 8 planets in a row, ending with the small blue one on the far right. Beside it, a full entry: diameter, mass, moons, wind speed, temperature. It reads exactly like the others. It should not. Every number in it comes from one afternoon in 1989, when a single spacecraft passed Neptune for a matter of hours and then left forever. And when telescopes finally got good enough to check a few of those lines, this is what came back. The storm large enough to hold the entire Earth has vanished, and nobody watched it go. The clouds have vanished, and the top of the atmosphere is now at just over half the temperature that afternoon recorded. Half. By the end of tonight, you will know exactly why Neptune is the scariest planet we will never reach, and it has almost nothing to do with the wind. Get cozy. If you are the kind of person who enjoys discovering that something you were taught has quietly expired, a quick like and subscribe genuinely helps this channel reach more curious minds like you. Because by the end of this, the words we know will have picked up a date stamp. Now let's ease down into this slowly. You have never seen Neptune. Not with your own eyes, and not by accident, and not on the clearest night of your life from the darkest place you have ever stood. Neptune is the only planet in our solar system that is invisible to the unaided human eye. Every other one of them has been available to every person who has ever lived. Mercury sits low in the dusk and the dawn. Venus is so bright it gets reported as an aircraft. Mars is orange and unmistakable. Jupiter and Saturn are steady and obvious, and have been tracked by every civilization that bothered to look up. Uranus is right at the edge of visibility. Technically possible, if you know exactly where to point, and the sky is perfect, and your eyes are good. And then there is Neptune, which is not there at all. Not faint, not difficult, simply absent from the sky that human beings evolved looking at. So the 8th planet is, for you personally, entirely hearsay. It is a thing you have been told about. And tonight I want to walk you very slowly through what exactly you've been told, and where those specific claims came from, and how old they are. Because the answer to that last question is the reason this video exists. Let me start with how Neptune was found, because the manner of its discovery turns out to be the first note in the whole piece of music. Neptune was not discovered by looking, it was discovered by arithmetic. In the early 1800s, astronomers had a problem with Uranus. Uranus had been identified as a planet in 1781, and for the decades afterward, people did the ordinary careful work of tracking it and predicting where it would be next. And it kept not being there, not by much, by a small, stubborn, absolutely unignorable amount. Uranus was being pulled by something. The French mathematician Urbain Le Verrier took that discrepancy and did something that still, nearly 2 centuries later, feels like it should not be allowed. He worked backwards. He assumed the existence of a planet nobody had ever seen, and he calculated what mass that planet would need to have, and where in the sky it would need to be, in order to produce exactly the deviations that Uranus was showing. He turned an error into an address. Then he wrote to Johann Gottfried Galle at the Berlin Observatory and told him where to point the telescope. Galle, working with Heinrich Louis d'Arrest, found the planet on his first night of searching in 1846. Not the first month, not after a patient survey. The first night. It was right where the mathematics said it would be. 17 days later, the English astronomer William Lassell found Neptune's largest moon, Triton, on the 10th of October, 1846. There is a footnote to this story that I love, and it is the kind of thing that tells you something about how astronomy actually works. Galileo saw Neptune. He recorded it in his observing notes in 1612, and again in 1613, as a fixed star, one small dim point among many, and he moved on. It was in his notebook for more than 200 years before anyone understood that he had drawn a planet. The 8th world in the solar system sat in the archive of the most famous observer in history, mislabeled, waiting. Now hold on to the shape of that discovery, because it is going to matter later in a way you will not expect. Neptune was found by inference. It was found by somebody noticing that a number was slightly wrong and refusing to let it go, and following the wrongness of that number all the way out to a new planet. That method worked so spectacularly that it became one of the permanent tools of astronomy. It is still in use tonight. It is, more or less exactly, how people are currently hunting for a possible ninth planet in the outer solar system. But there is a second half to that story, and the second half is a warning. We will come back to it. Here is what happened after 1846. Neptune took its place at the end of the diagram. It went into the textbooks, and onto the classroom posters, and into the little models made of painted polystyrene balls that get carried into school assembly halls. It became the last one, the blue one, the windy one. And for 143 years that was the entire relationship. A dot in a telescope, a set of orbital elements, a colour, and a name. Then, for a period of a few hours in 1989, a machine flew past it. That is the encounter. That is not the first of several encounters, or the beginning of a program of exploration, or the opening chapter of our understanding of the eighth planet. That is the whole thing. One spacecraft, one pass, one afternoon of measurements, and then the spacecraft kept going and never came back, and nothing has ever followed it. Nothing is scheduled to. So let me now pose the question this whole video is built around, and then deliberately not answer it. The title of this video says Neptune is the scariest planet we will never reach. And I want to be precise about that word, scariest, because there is an obvious version of it that is wrong. The obvious version is physical. The winds are the fastest in the solar system. The temperatures are brutal. There is no ground to stand on. The pressures would crush anything we could build. All of that is true, and we're going to go through it in detail, and none of it is what I mean. None of it can be what I mean, actually, just because nobody is going. There is no plan to send a person to Neptune. There is no plan to send a person anywhere near Neptune. A planet that no human will ever visit cannot frighten you the way a cliff edge frightens you. The danger is not the point. Something else is the point. And the something else has to do with the specific relationship between that one afternoon in 1989 and everything we have written down about Neptune since, and what has been discovered over the last few years by people who went back and looked carefully. By the end of tonight, you will know exactly why the eighth planet is the most unsettling object in the solar system, and it will have almost nothing to do with the weather there. For now, sit with the smaller strangeness. There is a world 4.5 billion kilometers away, 4 times wider than the one you're lying on, 17 times its mass, with a moon larger than Pluto and rings and a magnetic field, and weather systems the size of continents. It has been out there the whole time. It was out there while every human being who has ever lived looked up at a sky that did not contain it. It was in Galileo's notebook as a smudge. It was in Leverrier's calculations as a residual. And in the entire history of our species, we have been in the same room with it for less than 1 working day. Neptune completed its first full orbit of the Sun since its discovery in the year 2011. 1 Neptunian year is about 165 Earth years, 60,190 days, which means that the planet has only just finished going round once since we noticed it. And there is one more number I want to leave with you before we go anywhere near the flyby, because it quietly determines everything that follows. Neptune's axis is tilted about 28 degrees. That is remarkably close to Earth's own 23.5. It means Neptune has genuine seasons, driven by the same geometry that gives you summer and winter. But because the year is 165 of ours, each of Neptune's 4 seasons lasts more than 40 years. Take a moment with that. Every single season on Neptune is longer than the entire span of time we've had any close-up information about the planet at all. Whatever we learned in 1989, we learned it during one particular part of one particular Neptunian year, and the planet has moved on since, through a season change we did not watch, in a climate we have no baseline for. We will get to what that has done to the numbers. First, let us go to 1989 and see exactly what happened in those hours, and how much weight one afternoon can be asked to carry. Voyager 2 left Earth on the 20th of August, 1977. It reached Neptune on the 25th of August, 1989, 12 years in transit to arrive somewhere for a few hours. I want to lay out the mechanics of that encounter properly, because when people hear the phrase "we sent a spacecraft to Neptune," they tend to picture something like a visit, a period of residence, orbits, and instruments patiently building up coverage, and the slow accumulation of a data set. That is what happened at Jupiter with Galileo, and at Saturn with Cassini, and at Mars with a whole succession of orbiters that have now been photographing the place continuously for decades. Nothing like that happened at Neptune. What happened at Neptune was that an object moving at more than 16 kilometers per second went past, and while it went past, it looked. The closest approach was about 4,950 kilometers above Neptune's north pole, roughly 3,000 miles. That is the closest Voyager 2 came to any planet in its entire mission, closer to Neptune's cloud tops than the width of the Atlantic Ocean. And it is worth understanding why the trajectory was designed to bring it in that tight, because the answer is not what you would guess. It was not about Neptune, it was about Triton. Mission planners deliberately aimed Voyager 2 in over Neptune's north pole so that Neptune's own gravity would bend the spacecraft's path, pull it southward and downward, out of the plane it had been travelling in, and fling it toward a close pass of Neptune's largest moon about 5 hours later. The geometry of humanity's only visit to the eighth planet was partly chosen so that the same trajectory could deliver a look at its moon. Neptune's flyby was, in a real engineering sense, half a means to an end. There is an earlier version of that same trade, and it is even starker. Voyager 1 was the mission with the option to continue to Uranus and Neptune. In November of 1980, mission planners chose instead to route Voyager 1 close past Saturn's moon Titan, a decision that spent the trajectory and permanently removed Voyager 1 from any possibility of reaching the ice giants. It was, on its own terms, an excellent decision. Titan turned out to be one of the most interesting places in the solar system, and Voyager 1 found an opaque orange haze that took another 25 years and a European lander to see through. But the consequence is that Voyager 2 inherited the outer half of the tour alone. It arrived at Uranus on the 24th of January 1986, and at Neptune 3.5 years after that. One spacecraft, aging, running on a nuclear power source that was already declining, carrying instruments designed in the early 1970s, doing the only reconnaissance of the outer two planets that has ever been done. Now consider the conditions it was working in. At Neptune's distance, sunlight is roughly 900 times fainter than the daylight you're used to. NASA's own description of what that means is the best short sentence anybody has written about the planet. High noon on Neptune would seem like dim twilight to us, and Voyager 2's cameras were, by any modern standard, primitive. Taking a usable photograph in that light requires a long exposure. A long exposure from a platform moving at 16 kilometers per second produces a smear. The engineers solved this in flight with a technique they called image motion compensation. They had the entire spacecraft slowly rotate during each exposure, tracking its target the way you might pan a camera to follow a passing car, so that the target stayed still on the detector while everything else blurred. Every clear photograph you have ever seen of Neptune exists because somebody worked out how to make a nuclear-powered probe pivot at exactly the right rate, 4.5 billion kilometers away, with no possibility of a second attempt. Then there was the problem of hearing it. Radio signals weaken with the square of distance, and at Neptune, Voyager 2's transmitter was delivering a signal of almost inconceivable faintness by the time it reached Earth. To catch it, NASA linked the antennas of the Deep Space Network together with the Very Large Array in New Mexico and the Yasuda Station in Japan. An array of radio telescopes on multiple continents pooled to collect enough of one spacecraft's whisper to make out what it was saying. There was also the question of how much could be said at all. A spacecraft's downlink rate falls away with distance just as the signal strength does, and by the time Voyager 2 reached the ice giants, it was sending data home at a trickle, a rate slower than the dial-up modems that would come into people's homes a decade later. The team had to reprogram the spacecraft in flight, from Earth, to compress its images before transmitting them, deciding in advance which parts of which pictures were worth the bandwidth. Some of the photographs of Neptune exist in the form they do because an engineer made a judgment call about what could be thrown away, and every word of that conversation was 4 hours old. Light takes about 4 hours to cross the distance from the Sun to Neptune, and roughly the same to come back to Earth. Which means that during the encounter, Mission Control was watching events that had already finished, and any command they sent would arrive 4 hours into a future they could not see. There was no steering. There was no reacting. Every decision about what to point at, when, and for how long had been made in advance, encoded and uploaded, and then the spacecraft executed it alone in the dark while a room full of people on Earth waited to find out what had happened. Here is the part I find genuinely remarkable. It worked. In that one pass, Voyager 2 measured Neptune's mass properly for the first time. It measured the wind speeds. It found the magnetic field and characterized its bizarre orientation. It confirmed the rings, which had only been hinted at from Earth. It discovered 6 moons. It photographed a storm system large enough to contain the entire Earth. It measured the temperature of the upper atmosphere. it found that the planet radiates more energy than it receives, and then, 5 hours later, it turned to Triton and photographed something erupting on the coldest surface anybody had ever measured. That is an extraordinary afternoon of work. It is one of the great single-day performances in the history of science. It is also, and this is the sentence I want to plant carefully, almost everything we have. Not most of it, not the foundation of it. When you look up Neptune's wind speeds tonight, you are looking at Voyager 2's measurement. When you read about the tilt of its magnetic field, that is Voyager 2, the ring names, the ring positions, the arcs, the moon count that stood for decades, the internal heat balance, the atmospheric composition, the temperature profile, Voyager 2, that afternoon, from a moving platform once. There has been no second opinion. There has been no follow-up campaign. There is no orbiter. Every space telescope and every large ground-based observatory since has been able to look at Neptune, and they have, and we will get to what they found, and it is significant. But a telescope at a distance of 4.5 billion kilometers cannot measure a magnetic field where the field actually is. It cannot sample an atmosphere. It cannot weigh the interior. Those things require being there, and being there has happened once. There is a human footnote to all of this that is worth a moment, because it shows how thin the margins were on the ground as well as in space. The credit for Neptune's discovery was disputed for the better part of a century and a half. An English mathematician named John Couch Adams had performed comparable calculations independently, and had them in hand before Leverrier's prediction reached Berlin, but the astronomers he approached did not act on them with any urgency, and the search that would have found the planet from England never properly began. The result was a long, occasionally bitter argument about who deserved the planet, an argument conducted, remember, about an object that neither man had seen and that would not be examined at close range for another 143 years. Two people can spend their lives fighting over the discovery of a world, while the world itself remains a point of light. I said at the start that the manner of Neptune's discovery would matter. Here is the first instalment of that. Leverrier found Neptune by refusing to accept a number that was slightly wrong. That is the highest form of the scientific instinct. You do not let a discrepancy sit. But a discrepancy can only be noticed if somebody is measuring the thing repeatedly. Uranus was measured over and over for decades by many people, which is how the error became visible. Neptune has been measured up close exactly once, and a single measurement, however good, has a property that is easy to overlook. It cannot disagree with itself. There is nothing to compare it to. It sits in the reference tables unchallenged, not because it has been confirmed, but because there has never been anything in a position to contradict it. So the file on Neptune was opened in 1989, filled in a matter of hours, and closed. And Voyager 2 is still out there, still transmitting, still the only machine that has ever been near the planet, its power dropping by a few watts each year, its instruments being switched off one at a time to conserve what is left, its mission expected to end sometime in the early 2030s, which raises a question we're going to have to face before the end of tonight. What happens to the only witness's testimony when the witness dies and nobody was sent to take a second statement? But before that, we should find out what Voyager 2 actually saw, and the first thing it saw makes no sense at all. Neptune has the fastest winds in the solar system. That is the fact everyone knows, and it is usually delivered as a piece of trivia, one of those superlatives that gets printed in a box in the corner of a page. Fastest winds. Next fact. I would like to slow down on it, because when you put the number next to the conditions it occurs in, it stops being trivia and becomes a genuine problem in physics. The winds on Neptune drive clouds of frozen methane across the planet at speeds above 1,200 miles per hour, more than 2,000 kilometers per hour. NASA's own comparison is that Neptune's winds can be 3 times stronger than Jupiter's and 9 times stronger than Earth's, and that the most powerful winds on Earth reach only about 250 miles per hour, or 400 kilometers per hour. Sit with that for a second. The strongest wind ever recorded on this planet, the sort of wind that removes buildings from their foundations and strips bark from trees, would be, on Neptune, a mild afternoon. Something to be described as calmer than usual. But the speed is not actually the interesting part. The interesting part is the energy. Wind is not a substance. Wind is a symptom. Air moves because energy is being put into it somewhere and has to go somewhere else. And on Earth, Effectively, all of that energy comes from the sun. Sunlight lands on the ground and the ocean, warms them unevenly, and the atmosphere redistributes that unevenness. Every hurricane you have ever seen on a satellite image is solar energy in transit. The sun delivers about 1,361 watts per square meter to the top of Earth's atmosphere. That is the budget. Everything the weather does, it does with that. At Neptune, the budget is about 1.5 watts per square meter. Not 1.5% of Earth's. 1.5 watts against 1,361. That is roughly 1/900th as much light and heat arriving at the top of the atmosphere. It is the same figure as the brightness comparison. High noon on Neptune would look like dim twilight to us, expressed as power instead of illumination. So here is the situation. You have a planet receiving about 1/900th of the solar energy that drives Earth's weather, and it has weather 9 times more violent. Whatever is happening in Neptune's atmosphere, it is not being paid for by sunlight. It cannot be. The numbers are not close enough to argue about, and it gets stranger because of a word that appears in NASA's own one-line description of the planet. Dark, cold, and whipped by supersonic winds. Supersonic, not extremely fast, faster than sound. The speed of sound is not a fixed number. It depends on what the sound is travelling through and how hot that medium is. Sound moves faster through warm air than cold air, and faster through some gases than others. On Earth, at sea level, in ordinary conditions, it is around 1,230 kilometers per hour. In the frigid hydrogen and helium at the top of Neptune's atmosphere, it is lower, and the fastest jets on Neptune exceed it. Take a moment to picture what that means, physically, at the cloud tops. There is a place in this solar system where the weather is moving faster than the weather can be heard. Any disturbance, any pressure change, any thunderclap, any sound of any kind, cannot outrun the flow it is embedded in. Information in that atmosphere cannot travel upwind. There is a permanent planet-wide condition of things arriving before the sound of them arrives. I want to make sure this is not just an image, because it has a real consequence. In a supersonic flow, shock waves form. You cannot have smooth adjustment. You get discontinuities, sharp fronts where conditions change almost instantaneously across a very thin boundary. That is what a sonic boom is. It is why the physics of a supersonic aircraft is a different discipline from the physics of a slow one. Neptune's equatorial atmosphere is, in places, in that regime, not for a moment during a storm, as a standing condition. Then there is the direction, which is the part that gets left out of the trivia entirely. Neptune's most powerful winds blow backwards. In a broad band around the equator, the flow runs retrograde, against the planet's own rotation, while at higher latitudes the winds run prograde with the rotation. So Neptune is not a ball of gas being dragged along by its own spin. It is a ball of gas whose equatorial region is actively moving the other way at more than 2,000 kilometers per hour on 1.5 watts per square meter for as long as anybody has been able to check. There is a subtlety buried in the phrase "against the planet's own rotation" that is worth pulling out, because it exposes how much of this description is built on inference rather than observation. To say that a wind blows backwards, you need to know which way the planet turns and how fast. On Earth that is easy. You pick a rock, you watch it come back round. Neptune has no rock. It has no surface at all, and every visible cloud is being carried by the very winds you're trying to measure. So the clouds cannot tell you the rotation rate of the planet. They can only tell you the rotation rate of themselves. The way around this is to use the magnetic field. A planet's magnetic field is generated in its interior, so if the field is tilted relative to the spin axis, its radio signature sweeps around like a lighthouse beam, and the period of that sweep gives you the rotation of the deep interior. That is where Neptune's 16-hour day comes from. It is not a measurement of the planet's outside. It is a measurement of the planet's inside taken by radio, once, during one pass, and everything we say about winds being retrograde or prograde is quoted relative to it. Which is where I have to be honest about how short, as long as anybody has been able to check, actually is. Those wind measurements come from tracking cloud features across the disk of the planet and timing how far they move. Voyager 2 did that during the flyby, using the cloud bands and the dark spots and a bright, fast-moving feature in the southern hemisphere that the team nicknamed Scooter, because it went round the planet in about 16 hours and kept scooting ahead of everything else. The wind field of Neptune, the one in the textbooks, the one I have just described to you, was derived from watching a handful of markings move during a single pass. There is nothing wrong with the method. It is the same method used at Jupiter and Saturn, but at Jupiter and Saturn it has been done thousands of times, over decades, by orbiters and telescopes, and the results have been checked against each other and refined and occasionally corrected. At Neptune, it was done once, in one afternoon, using features that, as we will see later, have since disappeared. So what is driving the winds, if it is not the Sun? The answer, which we will take apart properly in the next part, is that Neptune has its own heat. The planet radiates significantly more energy into space than it absorbs from sunlight, which means there is a source of energy inside it, and that source is more than sufficient to power an atmosphere. Convection driven from below, hot material rising, cool material sinking on a rotating body, is entirely capable of producing banded jets at these speeds. That is the working explanation, and it is almost certainly correct in outline. But notice what it does to the character of the thing. Weather on Earth is a surface phenomenon. It is what happens when the outside of a planet is warmed unevenly by an external star. It belongs to the boundary between the world and the sky. It is, in a sense, a conversation between the Earth and the Sun. Weather on Neptune is not that. If the driving energy is internal, then those supersonic winds are not a response to the Sun at all. They are the outer expression of something happening deep inside a body we have never sampled, the visible end of a process whose origin is thousands of kilometers beneath the cloud deck, under pressures we can only reproduce for nanoseconds in a laboratory. The fastest winds in the solar system are exhaust. I should add one detail about scale here, because it changes how the picture sits in your head. Neptune is about 4 times the width of Earth, 49,528 kilometers across the equator, which NASA renders memorably as, if Earth were the size of a nickel, Neptune would be about the size of a baseball. It carries roughly 17 times Earth's mass, and it is the densest of the 4 giant planets, which is an odd distinction for a world with nothing solid in it. Because that mass is packed into a body of that size, the gravitational pull at the cloud tops works out at around 11 meters per second squared, very slightly stronger than Earth's 9.8. That comparison produces one of the most quietly disorienting facts about Neptune. If you could somehow be suspended at the level of those clouds, your body would report almost exactly the weight it reports right now, in the chair or the bed you are in. Everything else about the situation would be lethal and unrecognizable, and the one sensation your inner ear would confirm as normal is the pull downward, toward a down that has nothing at the bottom of it. And here is the thought I would like to leave you with before we go inside the planet. When you look at that famous photograph of Neptune, the deep blue one, with the bands and the dark oval, you are not looking at a planet's weather. You're looking at the outside of a machine from a distance in poor light for one afternoon and inferring the machine from the pattern on its casing. Nobody has ever looked inside. Nobody has measured the source of the energy that produces the fastest wind we know of anywhere. But we can say, with real confidence, that the source exists, because Neptune is warmer than it has any right to be, and that is not a subtle effect. It is a factor of 2.5, and the reason we know it is not an error is the strangest part of all. There is a control case sitting right next door, and it comes out the other way. Neptune is losing more heat than it is being given. That is the measurement, and it is not marginal. The planet radiates something like 2.6 times the energy it absorbs from sunlight. Put another way, its internal heat flow amounts to roughly 160% of the solar power it takes in. So of all the energy leaving Neptune, well over half of it never came from the Sun at all. There is nothing scandalous about a planet having internal heat. Earth has it. Radioactive decay in the rocks beneath you, plus leftover warmth from the planet's formation, produces a slow outward trickle that drives plate tectonics and volcanoes and keeps the outer core molten. But Earth's internal heat flow is a rounding error against the sunlight it receives, a fraction of a percent. It shapes the geology and does essentially nothing to the weather. The giant planets are different. Jupiter and Saturn both radiate substantially more than they absorb, and the reason is reasonably well understood. They are enormous. They are still slowly contracting under their own gravity, and gravitational contraction releases heat. A planet 300 times the mass of Earth has a great deal of stored energy to give up, and it gives it up over billions of years. Neptune is 17 Earth masses. It is not Jupiter, and yet, proportionally, it is running one of the largest energy surpluses in the solar system. Now here is the part that turns this from a curiosity into an open wound in planetary science. Uranus should behave the same way. Uranus and Neptune are, to a first approximation, the same planet twice. Uranus is very slightly wider. Neptune is slightly heavier and denser. They are both classed as ice giants, mostly a hot dense fluid of water, methane and ammonia over a small rocky core, with a hydrogen and helium envelope on top. They formed in the same region of the same disk at the same time, out of the same material. If you were handed the two of them as a physics problem, you would expect their answers to match. Uranus is roughly 1.5 billion kilometers closer to the Sun than Neptune. It receives well over twice as much sunlight. So Uranus should be the warmer of the two by a comfortable margin. Uranus has the coldest planetary atmosphere ever measured in the solar system. And when you look for the internal heat that should explain how it stays that cold, you cannot find it. Uranus's energy balance, the ratio of what it emits to what it absorbs, has been measured, and one published upper limit puts it at about 1.14, which is to say, within the uncertainties, Uranus may be radiating essentially exactly what it receives, and nothing more. No surplus, no furnace, a planet with almost no internal heat leaking out at all. So the two nearly identical worlds have arrived at opposite thermal states. One is running at 2.6, the other is running at something indistinguishable from 1, and the colder one is the one closer to the fire. It is worth pausing on how a number like that is even obtained, because the method has a weakness that matters. To work out a planet's energy balance, you need two quantities: how much sunlight it absorbs and how much heat it emits. The second is measured in the infrared. The first requires knowing precisely how much of the incoming light the planet reflects away, rather than takes in, a quantity called the bond albedo. And to measure that properly, you have to see the planet from angles that Earth never provides. You need to look at it from the side and from behind, catching the light it scatters forward. There is only one way to get those angles, which is to be out there. The energy balances of Uranus and Neptune rest to a significant degree on measurements. Voyager 2 made during its 2 flybys, and researchers have continued to revisit and revise those figures decades later, using the same 40-year-old data. For a sense of the absolute temperatures involved, Neptune averages about minus 201 degrees Celsius at the level where the pressure equals sea level pressure on Earth. Uranus, closer in, reaches lower still, the coldest planetary atmosphere on record, and both planets, it is now widely thought, formed nearer the Sun than they are today, and migrated outward about 4 billion years ago, which means their present distances are not even the distances they were assembled at. This is what makes Neptune's heat a genuine anomaly rather than an interesting figure. If Neptune were the only ice giant, you would simply say, ice giants retain formation heat. Fine, next question. But the control experiment exists. Nature ran the test twice with the same ingredients and got 2 different results, and nobody can tell you why with confidence. There are candidate explanations, and it is worth walking through them, because the shape of the candidates tells you something about the shape of the problem. The first candidate is a giant impact. Uranus is tipped over on its side. Its axis is tilted about 98 degrees, so it effectively rolls around its orbit rather than spinning upright. The standard explanation for that tilt is a collision, early on, with a body large enough to knock the entire planet over. A collision like that would also do violence to the interior, and one idea is that it either stripped away the outer layers where heat was stored, or, more interestingly, stratified the inside, sorted the material into layers of different composition that will not mix. That second version matters, because of what stratification does. Convection is how heat gets out of a fluid body. Hot material rises, cools, sinks, and the cycle carries energy upward. But convection requires that the material be able to move freely. If the interior is divided into layers of different composition, with a heavy layer beneath a light one, the layers refuse to exchange places. The heat cannot rise. It is not that the heat has gone, it is that the heat has been sealed in. This is called convective inhibition, and it has been studied specifically as a way to make Uranus and Neptune come out differently. If Uranus's interior is compositionally layered, and Neptune's is not, or is layered differently, then 2 planets with similar amounts of stored heat will leak it at wildly different rates. Uranus would be a thermos flask, Neptune would be a radiator. Notice something about that explanation. It does not say Uranus is cold because it has no heat. It says Uranus may be full of heat that cannot get out. If that is right, then the difference between the two ice giants is not a difference in energy content. It is a difference in internal architecture, in the arrangement of layers, thousands of kilometers down, in matter at pressures we can barely reproduce. And here we arrive at the boundary that this entire video keeps running into. To distinguish between these explanations, you need to know the internal structure of the two planets, how the density is distributed, where the compositional boundaries sit, how much of the mass is in the core, whether there are stable layers and where. That information does not come from telescopes. It comes from measuring a planet's gravitational field with great precision, which requires a spacecraft in orbit, passing over the planet repeatedly, having its own motion tracked to within fractions of a millimeter per second as the planet's lumpy gravity tugs at it. That is exactly what the Juno mission has been doing at Jupiter since 2016, and it has rewritten the interior model of Jupiter. The core turns out to be diluted and fuzzy rather than sharply bounded, which nobody expected. It is what Cassini did at Saturn during its final orbits in 2017, diving between the planet and its rings specifically to weigh the inside. Neither Uranus nor Neptune has ever had an orbiter, not one. The two planets that pose the sharpest unsolved question about how planets retain heat are the two planets we have never weighed properly. And I want to stress how much rides on this, because it is not a parochial question about our own solar system. When astronomers survey planets around other stars, one of the most common types they find is a world in this exact size range. A few times Earth's radius, somewhere between rocky and gas giant. The most abundant category of planet in the galaxy, as far as we can currently tell, is not Earth-like and not Jupiter-like. It is Neptune-like. We have two Neptune-like planets within reach. We have flown past each of them once, and they disagree with each other about something fundamental. So when you hear that Neptune emits 2.5 times more heat than it receives, do not file it as a fun fact about a distant world. File it as this. The most common kind of planet in the universe has a heat problem. We have two local examples to study. They contradict each other, and we have never sent an orbiter to either. The winds are the visible symptom. That heat is the engine, and the engine is inside a place where water behaves in ways that had never been seen anywhere, by anyone, until a laboratory on Earth managed to make it for a few billionths of a second, decades after our only spacecraft had already gone by. Which brings us to what it would actually be like to go down there. And it does not end the way falling usually ends. Neptune does not have a surface. I have said that twice already, and both times I said it the way it is usually said. As a technical note, a caveat, something to acknowledge and move past. I would like to spend some time on it properly, because no surface is one of those phrases that we accept without ever picturing, and the picture is stranger than the phrase. Here is what the phrase actually means. Neptune's atmosphere is mostly hydrogen and helium with a small amount of methane, and as you go down it gets denser. It keeps getting denser. There is no level at which the gas ends and something else begins. The atmosphere gradually merges into water and other melted ices, and those merge into a hot dense fluid, and that fluid eventually reaches a small rocky core of roughly Earth's mass at the centre. From the outside inward, it is one continuous substance getting thicker. When scientists quote a temperature or a wind speed at Neptune's surface, what they mean is the level where the pressure happens to equal the air pressure at sea level on Earth. That is the 1 bar level, and it is a convention. It is a line drawn on a graph for the convenience of comparison. There is nothing there. If you were falling through it, you would not notice. So let me put you in it. You are at the cloud tops. It is dim, not dark, but dim, the light of a heavily overcast evening, because the sun here is 900 times fainter than the one you know, and it is a very bright star rather than a disk. The clouds are methane ice, and they are moving past you at a speed that has no equivalent in your experience, and because you are falling with them rather than through them, there is no wind in your face at all. The most violent atmosphere in the solar system feels, from inside it, like nothing. You fall. Your body reports normal weight. This world pulls at about 11 meters per second squared, a fraction more than home. Above you the cloud deck closes over and the light goes blue, then grey, then out. You keep falling. The gas thickens around you, degree by degree, and the temperature climbs, and the pressure climbs, and there is no boundary anywhere, no shoreline, no cloud floor, no membrane, nothing that could be described as arriving. You're waiting for something to happen, and the only thing happening is more. And then, somewhere you could not identify, even if you were watching instruments, the medium stops behaving like air. It is too dense to be pushed aside. It holds you. You have not landed. Nothing struck you. You're simply, gradually no longer falling, held up by a substance that was a gas above you, and will be an ocean below you, and is neither at the place where it stopped you. That is the end of the descent. Not impact. Suspension. Let me put some numbers along the path you just fell down, because the numbers are what make it more than a mood. Near the top, at the 1 bar level, the temperature is around minus 201 degrees Celsius. That is the figure quoted as Neptune's average, and it is the coldest part of the journey. Not the middle, not the bottom, the top. Descend, and both pressure and temperature rise together, the way they do in any deep atmosphere. Within a few hundred kilometers, you are into pressures of tens and then hundreds of times Earth's sea level pressure, at temperatures that have climbed through zero and kept going. Somewhere in there the methane cloud deck sits, and above it a haze layer whose exact composition is still argued about, and beneath it, models place clouds of hydrogen sulfide and ammonia, layers that have never been photographed because they are under an opaque lid. Keep going, and the pressures reach the hundreds of thousands of times Earth's. Temperatures reach thousands of degrees, and it is important to hold both of those facts at once, because the intuition they violate is a strong one. We associate high temperature with expansion, with boiling, with things flying apart. Down here it is the reverse. The heat is intense, and the material is compressed, and the compression wins. There is even a question about whether the outside of the planet is what we were shown. The famous portrait of Neptune, that deep, saturated, almost cobalt blue, is not what the planet looks like. The Voyager team enhanced the contrast of those images deliberately to bring out the cloud features against the disk, which was entirely reasonable and was documented at the time. But the enhanced version is the one that went everywhere. In 2024, researchers at Oxford reprocessed the original data and showed that Neptune and Uranus look far more similar to each other than the iconic pictures suggest. Neptune is a paler, greener blue, much closer to its neighbour. The most reproduced image of the eighth planet, the one on the poster in the classroom, is a version of the planet that was adjusted for legibility. It is not a hoax, and nobody hid anything. But it is worth knowing that even the colour required a correction, and the correction took 35 years. Now come back out and look at what that means for the project of understanding this planet, because it is not only a good thought experiment, it is the central engineering fact about Neptune. Every world we have studied properly, we have studied by landing on it or orbiting it low. Landing gives you the ground truth, the sample, the direct measurement, the number that is not inferred. On Venus, the Soviet Venera probes lasted minutes on the surface, and those minutes are worth more than decades of orbital speculation. On Mars, we have rovers that have been sitting on rocks for years. On Titan, the Huygens lander transmitted for 72 minutes from the surface, and that 72 minutes remains the only in-place measurement anybody has taken anywhere in the outer solar system. Neptune offers no such option. You cannot land on it. You cannot orbit inside it. The only way to get a direct measurement of the atmosphere is to drop a probe and let it fall, transmitting as it goes, until the pressure crushes it. This is not hypothetical. It has been done once, at Jupiter. In December of 1995, the Galileo mission released an atmospheric entry probe into Jupiter's clouds. It survived for just under an hour before the conditions destroyed it, and in that hour it returned the only direct chemical sampling of a giant planet's atmosphere that exists. Everything we know about the composition of a gas giant from the inside comes from that one descent into one planet at one location, which happened to be an unusually dry spot and therefore gave a slightly misleading answer about Jupiter's water content, a complication that took years to sort out. Every serious mission concept for Neptune includes a probe like that, and the entire in-place chemical record of the eighth planet would be whatever it managed to transmit before it stopped existing. Perhaps an hour from one point on one descent, forever. Sit with the asymmetry of that for a moment. Earth's atmosphere has been sampled billions of times, at every altitude, by balloons and aircraft and towers and satellites, continuously, for a century. Neptune's atmosphere has been sampled 0 times, not once, and the best case, the funded and successful and everything goes right case, is 1 hour, and a probe cannot come back. Neptune's escape velocity is around 23 kilometers per second. third highest of any planet, behind only Jupiter and Saturn. Anything that goes down is gone. There is no sample return from a world like this, not as a matter of expense or ambition, but as a matter of arithmetic. There is one more consequence of having no surface, and it is subtler than the others. A planet with a surface has a place where its history is recorded. Craters accumulate, rocks preserve their formation conditions, ice keeps a layered record of what fell on it. You can read a solid world backwards, which is why we can talk about what Mars was like 3 billion years ago with reasonable confidence, having been there. Neptune keeps no record. It is a fluid, in motion, continuously overturning. There is no stratum to read, no ancient surface to date, no crater count to calibrate against. Whatever happened to Neptune in the past, impacts, migrations, the whole violent early history of the outer solar system, has been stirred into homogeneity. The planet's only memory is its internal structure and its chemistry, how much heavy material sits where, what ratios of gases are dissolved in the envelope. Those are exactly the two things you cannot measure from 4.5 billion kilometers away. So the eighth planet is a body with no surface to stand on, no floor to fall to, no ground to sample, no strata to read, and no direct measurement of any kind ever taken within it. And yet we do have a fairly detailed picture of what is down there. It is a picture assembled from theory, laboratory work, and inference. It includes an ocean that cannot boil, a form of water that is solid and liquid at the same time, and something falling continuously through the dark that our best experiments say has to be diamond. None of it has been seen. All of it follows from physics we can test on Earth. Let us go down there properly. At least 80% of Neptune's mass is not atmosphere. It is a hot, dense fluid of water, methane and ammonia, sitting over a rocky core of roughly Earth's mass. So the planet you have been picturing as a ball of blue gas is, by weight, mostly an ocean thousands of kilometers deep, with no shore, no bottom you could stand on, and no top. NASA's public description of this layer is remarkable for how carefully it is phrased. Scientists think there might be an ocean of super-hot water under Neptune's cold clouds. It does not boil away because incredibly high pressure keeps it locked inside. Read that again slowly because there is a lot compressed into it. Water that is thousands of degrees, not warm, not near boiling, far past every temperature at which water on Earth turns to steam, past the temperature of molten lead, into ranges where things glow. And it is not steam. It cannot become steam, because boiling requires expansion, and expansion requires somewhere to expand into, and there is nowhere. The weight of the entire planet above it holds it down. Water at a temperature that should have torn itself apart into gas, pressed so hard that it has no choice but to remain a fluid. This is one of the places where everyday intuition about matter simply stops working. We learn as children that water has 3 states, and that they occupy a neat sequence: ice, then liquid, then gas, arranged by temperature. That sequence is not a law of water. It is a description of what water does at the pressure that happens to exist at the bottom of Earth's atmosphere. Change the pressure enough and the whole map redraws, and in the middle of Neptune the map redraws into something that has no everyday name at all. At the pressures and temperatures believed to hold in that deep layer, water is expected to enter a state called supersonic. Here is what happens to it. The oxygen atoms lock into a rigid crystal lattice, a solid, in the ordinary sense a fixed geometric framework, and the hydrogen atoms do not. The hydrogen ions break free and move through that lattice like a liquid flowing through a sponge, at high speed, in all directions. So the water is simultaneously solid and liquid. Not a mixture, not slush, not something halfway. The oxygen is a crystal, and the hydrogen is a fluid, in the same substance, in the same place, at the same time. I want to flag what happened with this idea, because the timeline is important to tonight's argument. Supersonic water was a theoretical prediction for years. It was created experimentally at high-pressure laboratories only in the late 2010s, pushed into existence for fractions of a second using shock compression, and confirmed. It is sometimes designated Ice 18, which is a lovely detail on its own. There are enough distinct crystalline forms of water known that we have run into the high teens naming them, and only a handful of those exist anywhere on Earth's surface. Supersonic water moved from speculation to laboratory fact, roughly 30 years after our only spacecraft flew past the planet, whose interior is supposed to be made of it. That has a consequence, and it is the sort of consequence that is easy to miss. When Voyager 2 passed Neptune in 1989, the people interpreting its data did not know this state of matter existed. They were building models of the planet's interior out of materials as they were then understood. Every model of Neptune's inside that predates the last decade was working from an incomplete inventory of the possible. Now let me tell you about the diamonds, because this is the part that sounds like poetry and is actually an experimental result. Neptune's fluid interior contains methane, carbon and hydrogen bonded together. Under enough compression, chemistry gets rearranged. The bonds that hold methane together become less favourable than other arrangements, and the carbon can separate out and crystallise. Carbon crystallised under pressure is diamond, and diamond is denser than the surrounding fluid, so it sinks. Diamond rain, continuously at depth throughout the planet for 4.5 billion years. For a long time this was an inference, a chain of reasoning about phase diagrams that seemed sound but had never been demonstrated. Then, in 2017, a team led by the physicist Dominic Krauss took it into a laboratory and did it. The work was done at the SLAC National Accelerator Laboratory in California, in collaboration with Lawrence Livermore National Laboratory. The target was a thin sheet of polystyrene, the ordinary plastic of a disposable cup, chosen deliberately because polystyrene is built from the same carbon and hydrogen as the hydrocarbons inside the ice giants. They hit it with an intense optical laser to drive a shockwave through it, generating for an instant the crushing pressures and temperatures believed to exist inside Neptune, and in that same instant they fired SLAC's X-ray free electron laser through the sample to see what the atoms were doing. The shock lasted nanoseconds. The diagnostic had to be timed to the shock front, because what forms in a shock is destroyed by the shock passing. What came back was a diffraction pattern, not a photograph of diamonds, but the unmistakable signature of a diamond lattice. Nearly every carbon atom in the original plastic had been incorporated into nanodiamonds, diamond structures a few nanometers across, almost complete conversion. In the instant the shock passed, the carbon in a disposable cup snapped into the most ordered arrangement carbon has. The results were published in Nature Astronomy on the 21st of August 2017. Later experiments extended the work using plastics containing oxygen to better match the water-rich chemistry actually expected in the planets, and found that adding oxygen made diamond formation easier rather than harder, which is a result that strengthens the planetary case considerably, because the real interiors are full of water. To give you a sense of what ice giant conditions means in laboratory terms, the experiment reached pressures on the order of 1.5 million times Earth's atmospheric pressure, at temperatures of several thousand Kelvin. Those are the conditions a few thousand kilometers down inside Neptune, held for a few billionths of a second in a target the size of a fingernail in California. How big the diamonds actually get inside a real planet is genuinely unknown, and the estimates span an uncomfortable range. At the small end, nanometers, the scale the experiment produced. At the speculative end, some models allow crystals to accumulate and grow as they sink, potentially reaching sizes that would be, if you could ever retrieve one, absurd. And in the most speculative versions of all, and I want to label this clearly as speculation rather than result, some interior models permit a layer of liquid carbon deep down, with solid diamond floating in it like ice on a pond. Diamond icebergs on a carbon sea. That is a model output, not an observation, and it should be held very loosely. But it is what the equations allow when you put in the numbers we think are correct. There is one more reason the two ice giants cannot simply be treated as interchangeable in any of this. Neptune is the densest of the 4 giant planets, which means models of its interior have less room for a large light hydrogen envelope than models of Uranus do. More of Neptune's mass has to be in the heavy fluid layer. Whatever chemistry is happening in that layer, Neptune has more of it. Now, this does not prove that it is raining diamonds inside Neptune tonight. What it does is remove the last honest reason to call the idea fanciful. Under the conditions we believe exist inside the planet, carbon does exactly what the prediction says it does. If the conditions are right, the rain is real. The only remaining uncertainty is whether the conditions are right, and the only way to find out is to go and measure them. But here is where the story stops being decorative and starts joining up with everything else in this video. Diamonds falling through a fluid do not just fall, they release energy. Any dense object sinking through a lighter medium converts gravitational potential energy into heat, and if that is happening continuously, at planetary scale, over billions of years, it is a heat source. It is one of the candidate contributors to Neptune's energy surplus, the 2.6 ratio we could not explain. And the process does something else too. Separating materials by density is how you build layers. Carbon precipitating out and settling inward leaves the fluid above it compositionally different from the fluid below it. That is stratification, exactly the kind of internal architecture in which some regions convect and others refuse to, in which heat can be trapped in one place and released in another. Which is precisely what is needed to explain the third anomaly, the one we have not properly examined yet. Because Neptune's magnetic field is not generated in a large convecting core the way Earth's is, the best current models say it is produced in a thin shell, sandwiched between layers that do not mix. Look at what has just happened to our list of unexplained things: the winds that sunlight cannot power, the heat that has no confirmed source, the magnetic field that is not centered on the planet. In the most joined-up version of the story, those are not three mysteries. They are one mystery, viewed from three angles: a planet whose interior has separated into layers that do not communicate with each other, and in which a form of matter we learned to make a few years ago is doing all the work. Every link in that chain is a model, not one of them has been measured in place, and the strangest of the three is the one we have been putting off. Because Neptune's magnetism is not merely unusual, it is the kind of unusual that makes you question whether the words we use for planets mean anything at all. You have a compass in your pocket. It is in your phone, and it works. And it works because Earth generates a magnetic field that behaves, to a good approximation, like a bar magnet buried at the center of the planet and lined up roughly with the axis of rotation. Roughly is doing some work in that sentence. Earth's magnetic axis is tilted about 11 degrees from its rotational axis, which is why magnetic north and true north are not the same place, and why anyone navigating properly has to correct for the difference. The field also wanders. The North Magnetic Pole has been drifting across the Arctic at a decent clip for decades, and every few 100,000 years on average the whole thing flips over. So even here, the neat picture is an approximation. But it is a good approximation, close enough that we built centuries of navigation on it, close enough that the planet's magnetic poles is a phrase with a stable, useful meaning. Now here is Neptune. Neptune's magnetic axis is tilted about 47 degrees from its rotational axis. Not 11, 47, nearly halfway to lying on its side relative to the spin, and the field is not centered on the planet. The effective center of Neptune's magnetic field is offset from the center of the planet by roughly 0.55 planetary radii. Take that in properly, more than half the planet's radius. If Neptune were a beach ball, the magnet inside it would not be at the middle. It would be more than halfway out toward the skin. Both of those measurements came from Voyager 2, in 1989, in a few hours. Put the tilt and the offset together and you get something that is not a bar magnet at all. The technical description is that Neptune's field is non-dipolar and non-axis symmetric. It does not have a clean two-pole structure, and it is not symmetric about any axis. Earth's field is a slightly crooked bar magnet. Neptune's field is not a bar magnet with an error in it. It is a different kind of object. The consequence, which Voyager 2 could observe but not explain, is that Neptune's magnetosphere, the enormous bubble of magnetic influence surrounding the planet, deflecting the solar wind, cannot hold a stable shape. Every 16 hours, as the planet rotates, that lopsided field swings around, and the entire magnetosphere reconfigures. It stretches, it twists, it presents a different profile to the oncoming solar wind, and then it does it again. There is no steady state. Neptune's magnetic environment is in permanent structural upheaval on a 16-hour cycle, and it has been for 4.5 billion years. I want to pause here, because this is where the word in this video's title starts to become the right word, and it has nothing to do with danger. We carry, all of us, a set of assumptions about what a planet is. Not scientific assumptions, deeper than that. A planet is a ball. It has a top and a bottom, a north and a south. It has an inside and an outside arranged concentrically. When you say the poles, you mean the ends of something. That structure feels less like a theory and more like a fact about shapes. But that structure is not a property of planets. It is a property of one planet, which happens to be the one we grew up on, and which happens to have organized itself unusually tidily. Neptune has not. At Neptune, the question, where is magnetic north, does not have an answer that stays put for one rotation. The field is centered somewhere that is not the middle. The geometry we regard as basic to the concept of a world is, out there, simply absent. You can see it in the aurorae, and this is my favourite demonstration of it, because it is visible. Aurorae happen where magnetic field lines funnel charged particles down into the atmosphere. On Earth, that is the poles, which is why you go to Iceland or Tromsø or Tasmania to see them, and why they are called the Northern and Southern Lights. Same on Jupiter, same on Saturn. Neptune's aurorae are not at its poles. They are at mid-latitudes, roughly the equivalent on Earth of where South America is. If you lived on Neptune, the lights would not be a thing you travelled north to see. They would be over the middle of the planet, because that is where the crooked off-centre field happens to come down. There is a further consequence of the offset that is worth spelling out, because it is not obvious. If the magnet is more than halfway out toward one side of the planet, then the strength of the field at the cloud tops is wildly different depending on where you stand. On the side where the magnetic centre is close, the field is strong. On the opposite side, it is weak. There is no single number for Neptune's surface field strength, because the concept requires a symmetry the planet does not have. The overall field is about 27 times stronger than Earth's, when measured as a total magnetic moment, but locally, at the cloud tops, it ranges from well below Earth's surface field to well above it, and the map is lopsided. Uranus, incidentally, is the same kind of strange in a different way. Its magnetic axis is tilted about 60 degrees from its rotation axis, and offset as well. Two ice giants, two badly behaved magnetic fields, both measured by the same spacecraft on the same tour, and both unlike anything else known. That is either a coincidence or a clue about how ice giants work, and there is no way to tell which without going back. So how do you generate a field like that? The leading answer is called a thin shell dynamo, and it is one of the more elegant pieces of reasoning in planetary science. Earth's field is produced in a large convecting outer core of liquid iron, a big region, deep down, churning. That produces a field with a clean dipole structure aligned near the rotation axis, because a large rotating convective region naturally organizes itself that way. If, instead, the electrically conducting fluid is confined to a thin shell, a relatively narrow layer, sandwiched between things that do not participate, the physics changes. The field that comes out is messier, less dipolar, and can be badly offset. And the models say Neptune's generating layer is at most about 0.3 planetary radii thick, sitting below the hydrogen and helium envelope and above an interior that is fluid but stably stratified. Stably stratified. That phrase should sound familiar. It is exactly the internal architecture the diamond precipitation would produce, and exactly the architecture that convective inhibition needs in order to explain the difference between Neptune's heat and Uranus's. And what is the conducting fluid in that shell? The current best candidate is the superionic water we talked about, the state with a rigid oxygen lattice and hydrogen ions flowing through it. Superionic water conducts electricity well, precisely because those hydrogen ions are free to move. But how well it conducts, and in which directions, depends on the geometry of the lattice they are moving through. Recent work has looked at what happens if that lattice is not neatly ordered but riddled with stacking faults and mixed arrangements. The answer is that the electrical currents become irregular too, and a dynamo running on irregular currents produces an irregular field, which gives you the most satisfying version of the explanation available tonight. Neptune's magnetism looks wrong because it is being generated by a form of matter whose structure is imperfect, in a layer that is thin because the planet has separated into strata, in a body whose strata may exist because carbon has been precipitating out of it for 4.5 billion years. That is a beautiful piece of reasoning. It connects the heat, the field, and the diamonds into one story. It also explains something we noted earlier without explaining, why Neptune's 16-hour day is a measurement of the planet's interior rather than its exterior. The rotation period comes from watching the radio signature of that tilted field sweep past. So the number we quote for the length of a Neptunian day is a byproduct of the very anomaly we cannot account for. It is also entirely unverified. Every element of it, the shell thickness, the stratification, the superionic layer, the lattice disorder, is a model constrained by two things: laboratory experiments on Earth and a magnetic field measurement made during one pass in 1989. And to test it, you would need to be there. You would need to fly repeatedly through Neptune's magnetosphere at different latitudes and distances, mapping the field in 3 dimensions over multiple rotations, the way Juno has been mapping Jupiter's since 2016, work which, incidentally, found Jupiter's field to be far weirder than anyone expected, with a concentrated patch near the equator that nobody predicted from flyby data. Flyby data. That is the whole point. Jupiter's field looked one way from flybys and another way from orbit. Neptune has only ever been seen from a flyby, and here is the fact that makes all of this sting, which we are going to spend the next part of this video circling before it lands properly. We have known since 1989 that Neptune's aurorae should exist. Everyone expected them, and for more than 30 years nobody could find them, not for want of trying, but because the search was being conducted using a number from that same afternoon, and the number had stopped being true. Triton orbits Neptune backwards. That is the fact that everything else about this moon hangs from, so let me be precise about what it means. Moons, as a rule, orbit in the same direction their planet spins. This is not a coincidence or a preference. It is a consequence of how moons form. A planet condenses out of a rotating disk of gas and dust, and the leftover material in that disk, which is rotating the same way, coalesces into moons. Same spin, same direction, roughly the same plane. Jupiter's 4 large moons do this. Saturn's do, ours does, Triton does not. Triton goes round Neptune in the opposite direction to Neptune's rotation, a retrograde orbit, inclined about 157 degrees to the planet's equator. It is the only large moon in the solar system that does this, and there is no way to form a large moon in a retrograde orbit out of a planet's own disk. The geometry forbids it. So NASA's own inference is the only one available. Triton may once have been an independent object that Neptune captured. Think about what that sentence is claiming. Triton is not Neptune's child. It is Neptune's prisoner. Triton is about 2,700 kilometers across, making it the 7th largest moon in the solar system, bigger than Pluto. It contains the overwhelming majority of all the mass in orbit around Neptune. Every other Neptunian moon put together is a rounding error beside it, and the strong likelihood is that it formed out in the Kuiper belt as one of the larger bodies of that population, minding its own business in a wide, slow orbit around the Sun, and then came too close to Neptune and was caught. Capture is not easy. If an object simply falls toward a planet, it whips around and leaves again with the same energy it arrived with. That is how gravity works when only 2 bodies are involved. To capture something permanently, you need to take energy out of the encounter. The favoured explanations for Triton involve either drag through the gas of Neptune's early surrounding disk, or, the more dramatic possibility, that Triton arrived as one half of a binary pair, and the encounter with Neptune broke the pair apart, ejecting the partner and leaving Triton behind with less energy than it came in with. If that second version is right, then somewhere out there is another large Kuiper belt object that was thrown clear of the solar system, or into a wildly different orbit at the moment Triton was taken. There is a piece of supporting evidence for the violence of that event, and it is in the rest of the Neptunian system. Nereid, another Neptunian moon, has one of the most eccentric orbits of any moon known, a stretched, lopsided path that swings enormously in and out. Orbits like that do not happen quietly. They are read as damage, the gravitational wreckage left behind by whatever arrived and rearranged everything. So the Neptunian system is not a system that grew up together. It is a system that survived an intrusion. Now let me tell you what Voyager 2 found when it looked at this captured world, because it is the single most unexpected result of the entire encounter, and remember, the whole flyby geometry was chosen to make this look possible. Neptune's gravity bent the spacecraft's path southward, specifically so that about 5 hours after closest approach to the planet, it would sweep past Triton. Triton's surface temperature is about 38 Kelvin, that is minus 235 degrees Celsius, or minus 391 degrees Fahrenheit. It is among the coldest surfaces ever measured anywhere in the solar system. At that temperature, nitrogen, the gas that makes up most of the air you're breathing right now, that is frozen solid, lying on the ground as pale ice, and Voyager 2 photographed it erupting. Dark plumes were rising off the surface, climbing nearly 8 kilometers, about 5 miles, and then bending over at altitude where a thin nitrogen wind caught them and streaking downwind for as much as 150 kilometers, laying long dark stains across the pale ground. Mission scientists described it as the biggest surprise of the flyby. On the coldest surface anyone had ever measured, something was actively venting into space. Let me put you there for a moment. You're standing on frozen nitrogen. It is pale, faintly pink and slightly translucent, and it does not creak under you because nothing at 38 Kelvin creaks. The sun is a very bright star and gives no warmth of any kind. Neptune hangs enormous and dim above you, a pale blue-green disk many times the size the moon appears from Earth, and it does not rise or set the way a moon should because you are looking at it from a world that goes the wrong way round. Everything is still. It is the stillest place a human being could stand, and then, across the plain, a column of dark material rises. It goes up smoothly and it keeps going, 1 kilometre, 3, 5, nearly 8, because there is almost no gravity to stop it, and almost no air to slow it. At the top it meets a wind you cannot feel, thinner than anything you would call atmosphere, and it turns. It bends over and draws out sideways, and it keeps drawing out, for 100 kilometres and more, a dark line ruled across the ice. There is no sound. There has never been a sound here, and the coldest ground ever measured is throwing material at the sky. The favoured explanation for those plumes is quietly wonderful, because it requires almost nothing. It is called a solid-state greenhouse effect. Nitrogen ice is transparent, so the faint sunlight, 900 times weaker than ours, passes through the surface layer and is absorbed by darker material a metre or two down. That darker material warms very slightly. Slightly is enough. Nitrogen sublimates at these temperatures with only a few degrees of encouragement, and the gas produced has nowhere to go, so pressure builds beneath a sealed lid of ice until it finds a weakness and ruptures. That is all it takes. Weak sunlight, a transparent lid, and time. The most energetic-looking process on the coldest surface in the solar system is powered by twilight. The plumes are not the only thing about that surface which has no counterpart anywhere else. Much of Triton is covered in a terrain type that has been given the least scientific name in planetary geology, cantaloupe terrain. It is a landscape of closely packed dimples and rounded depressions, 30 or 40 kilometres across, crowding each other like the rind of a melon. Nothing else in the solar system looks like it. The leading explanations involve diaporism, blobs of lower density material rising slowly through denser ice over long periods, the way lava lamps work, but in solid ice at temperatures near absolute zero. That explanation is a hypothesis about a process nobody has watched, inferred from photographs of one hemisphere taken during a single pass. What is not in doubt is that the surface is young. Triton has remarkably few impact craters. In a solar system where every ancient surface is saturated with them, an uncratered surface means one thing. The ground has been renewed, and recently in geological terms. Something has been resurfacing Triton. There is a candidate for what? Triton's density is around 2 grams per cubic centimetre, which is high for an icy moon. It implies substantially more rock in the mix than most of Jupiter's or Saturn's icy satellites. More rock means more radioactive material, which means more internal heat from radioactive decay. Add whatever tidal heating remains from the ongoing circularization of a captured orbit, and it becomes plausible, not established plausible, that Triton has a liquid water ocean beneath its ice, an ocean at 38 Kelvin on the outside, on a body that arrived from somewhere else. And there is a way of framing Triton that I find quietly extraordinary. If Triton really is a captured Kuiper Belt object, then the best observed large body of the trans-Neptunian population is not any of the thousands catalogued out there in wide orbits. It is the one that happens to be in orbit around Neptune, where a spacecraft went past it once. Our clearest look at the outer solar system's building blocks is a look at a specimen that was pulled out of that population billions of years ago and has been heated and reworked ever since, which is to say, a specimen that is no longer representative of the thing we want to study. Triton also has an atmosphere, thin, nitrogen-dominated, discovered by Voyager during that same pass. It has been detected repeatedly from Earth in the decades since, mostly by watching Triton pass in front of distant stars and measuring how the starlight dims at the edges. And here is the sentence from NASA's own description of it, which I want to read to you exactly because of what it does not say. Triton's thin atmosphere has been detected from Earth several times since and is growing warmer, but scientists do not yet know why. Growing warmer. Nobody knows why. That is the state of knowledge about the atmosphere of the 7th largest moon in the solar system in the 2020s, and Triton is not going to be there forever. Because it orbits retrograde, Tidal interaction with Neptune works against it rather than for it. Our own moon orbits in the same direction Earth spins, and the tidal exchange between them pushes the moon slowly outward, a few centimeters a year, gradually escaping. Triton's retrograde motion reverses the sign of that entire process. Neptune's tides are dragging Triton inward. The moon is spiraling down. The timescale is enormous, billions of years, so this is not a countdown in any human sense, but the destination is not in doubt. Eventually Triton will cross the Roche limit, the distance at which a planet's tidal forces exceed a moon's own gravity holding it together, and it will be pulled apart. And when it is, the debris will spread into a ring system that would briefly make Neptune the most spectacular ringed planet in the solar system. A set of rings far grander than Saturn's, made from the corpse of a captured world. So Triton is a Kuiper belt object that was seized, is being slowly reeled in, has an unexplained warming atmosphere, and erupts on the coldest ground we have ever measured. Here is the number I have been saving. Voyager 2 imaged about 40% of Triton's surface. 60% of it, the majority of the largest captured world in the solar system, a body bigger than Pluto, has never been photographed at any useful resolution by anything, ever. It is not that the images are low quality. There are no images. That ground has never been seen. There was a plan. A mission called Trident was proposed within NASA's Discovery program, a flyby aimed at the 2030s, designed to check whether Triton harbours a subsurface ocean and, crucially, to photograph the hemisphere nobody has seen. It was a strong proposal, and it was not selected, which means that if you want to know what is on the far side of Triton, the honest answer available tonight is that nobody knows, nobody's going to find out soon, and the last time anybody got a look at the near side, the photographs were being taken by a spacecraft that will be dead within about a decade. And that is before we get to what has happened to Neptune itself since. Neptune has rings. Most people do not know this, and the reason most people do not know it is that they are dark, faint, dusty, and were only properly confirmed during that one flyby, after tentative hints from Earth in the 1980s, when astronomers watching Neptune pass in front of a star saw the starlight flicker slightly before and after the planet itself blocked it. There are at least 5 main rings, and they are named after the people tangled up in the planet's discovery and early study, which is a nice touch, and also a reminder of how recently all of this was assembled. Working outward from the planet, they are Gala, at about 41,900 kilometers from Neptune's center, Leverrier at 53,200, Lassell at 55,400, Arago at 57,600, and Adams, the outermost, at about 62,930 kilometers. They are thought to be young and short-lived, which is a standard finding for ring systems and worth a moment of its own. Rings are not permanent features of planets. They are debris, they degrade, they get dragged down or dispersed, and they need replenishing. When we say Neptune's rings are young, we mean the system we see cannot have looked like this for the whole history of the planet, and will not look like this for much longer, where much longer is measured in tens or hundreds of millions of years. But the genuinely strange thing about Neptune's rings is not the rings, it is what is inside the outermost one. The Adams ring contains 4 discrete clumps of material. They have names, given by the French team involved in the occultation work, and the names are wonderful. Liberté, Égalité, Fraternité, and Courage. Liberty, equality, fraternity, and courage. 4 bright arcs of dust sitting in one narrow ring, 62,000 kilometers out from a planet that nobody has visited since 1989. Here is the problem with them. They should not exist. Orbital mechanics is unforgiving on this point. Material at slightly different distances from a planet orbits at slightly different speeds. Closer means faster, always. So any clump of material in a ring has an inner edge moving faster than its outer edge, and it gets sheared. Within a handful of orbits, a clump becomes a streak, and within a few more, the streak becomes a uniform band. This is not a subtle effect that takes ages. It is fast and reliable, and it is why rings look like rings and not like beads. Neptune's arcs have not sheared out. They have been sitting there as distinct concentrations holding together for as long as anybody has been able to observe them. NASA's own summary of the situation is unusually direct, and I want to quote it, because official science communication does not often use this kind of language. The arcs are strange because the laws of motion would predict that they would spread out evenly rather than stay clumped together. The current explanation is a moon called Galatea. Galatea orbits just inside the Adam's ring, and the proposal is that its gravity produces a resonance, a repeating pattern of gravitational nudges that arrive at the same points in the ring every orbit, corralling the material and preventing it from spreading. The technical term is shepherding, and the imagery is apt. A small body going round and round, keeping a flock together by repeatedly pushing at its edges. It is a good explanation. It is also, and I want you to notice the pattern by now, a mechanism that has never been observed operating. It is a model that reproduces the observation, built from a single flyby's worth of data about the positions and masses involved. And there is a wrinkle. The arcs have not been stable in the way a clean shepherding model predicts. Over the decades since, observations from Earth and from space telescopes have found that the arcs have shifted, changed in brightness, changed in position, and some of them have faded substantially. The mechanism that is supposed to be holding them in place does not fully account for what they have actually been doing. That is not a scandal, it is normal science with insufficient data. But it is one more entry on a growing list. It is worth saying what these rings are actually made of, because it is not what Saturn's are made of, and the difference matters. Saturn's rings are overwhelmingly water ice, bright and reflective, which is why they are visible in a cheap telescope from a suburban garden. Neptune's rings are dark and dust-rich, reflecting very little light. Some of the components are narrow and reasonably well defined. Others are broad, faint sheets of material that barely register. When the James Webb Space Telescope photographed Neptune in 2022, one of the results that got the most attention among planetary scientists was that it produced the clearest view of those rings in more than 3 decades, showing not just the bright narrow rings but the fainter dust bands as well. That is worth pausing on. The best images of Neptune's ring system between 1989 and 2022 were the ones taken during the flyby. 33 years, and the next real improvement came from a telescope 1.5 million kilometers from Earth, pointed at the planet for a few hours. The moons deserve a mention too, because they tell the same story in miniature. Neptune has 16 known moons. 6 of them were discovered by Voyager 2 during the flyby, a single afternoon that more than tripled the known satellite count of the planet. And the most recent addition came from a different direction entirely. In 2019, an announcement was made about a very small moon that had been teased out of Hubble Space Telescope images taken of the Neptune system between 2004 and 2009. It had been found by Mark Showalter, who pulled it out of the data by combining many faint exposures, a moon about 34 kilometers across, far too small and dim to have been noticed any other way. It was named Hippocamp after the seahorse of Greek mythology. Hippocamp's story is a small tragedy told in orbital parameters. Its size and its position suggest it is a fragment, a chip knocked off the much larger moon Proteus by a comet impact, billions of years ago, which then settled into its own orbit nearby. It is not a moon in the sense of being a body that formed. It is a piece of something that was hit, and so the pattern of the Neptunian system completes itself, a captured prisoner of a moon holding almost all the mass. Another moon on a wrecked, stretched orbit that reads as collateral damage, a tiny moon that is a fragment of a bigger one, rings that are temporary, arcs in those rings that violate the laws of motion unless a shepherd is invoked, and that do not quite behave the way the shepherd predicts. None of it looks designed. All of it looks like the aftermath of things happening to a planet. And there is one more thing hiding in that moon count. 16 is the number for Neptune. Jupiter's confirmed satellites now run into the 90s, Saturn's past the hundreds, because both planets have been surveyed intensively and repeatedly from Earth and from orbit by dedicated campaigns. Neptune has not. Nobody seriously believes 16 is the true number of objects in orbit around the 8th planet. It is the number that has been found so far, by a flyby and by a handful of people carefully processing telescope archives in their spare time. And every single number in the paragraph you just heard traces back either to that one flyby, or to somebody squeezing a faint signal out of a telescope from 4.5 billion kilometers away decades later, and finding that things were not quite where the flyby said. Which brings us, at last, to the part of this video that I think actually matters, because so far I have been describing a strange planet. Now I want to describe what has happened to our description of it. In 1989, Voyager 2 photographed a storm in Neptune's southern hemisphere large enough to contain the entire Earth. A dark oval, sharply defined against the banded cloud deck, with a bright companion cloud riding alongside it. It was named the Great Dark Spot. The naming tells you exactly how it was understood. Jupiter has the Great Red Spot, which has been continuously observed for centuries and is one of the most stable features in the solar system. So Neptune had its own great spot, its own permanent signature, the feature by which the planet would be recognized. It went into the textbooks that way. It is in the image that most people, if asked to picture Neptune, are picturing right now. In the mid-1990s, the Hubble Space Telescope looked at Neptune. It was gone, not faded, not shrunk, not displaced, absent. The defining feature of the eighth planet had ceased to exist somewhere in the 5 or 6 years since anyone had been able to look closely, and nobody saw it happen, and there is no record of it happening. Other dark spots have since appeared, in other places, and disappeared again. That is the pattern. Neptune's dark vortices last a few years. Jupiter's Great Red Spot has lasted for centuries. Same category of feature, wildly different lifetimes, and we assumed the former was the latter because we had seen it precisely once. A planet is not a photograph. That is the sentence I want to hand you here, and I will come back to it. We have a photograph of Neptune. We have been treating it as a planet. In 2023, something happened that had never been done before. A dark spot on Neptune was observed from the ground. A team led by Professor Patrick Irwin at the University of Oxford used the Multi-Unit Spectroscopic Explorer, MUSE, on the European Southern Observatory's Very Large Telescope, and rather than simply imaging the spot, they split the reflected sunlight from it into a full three-dimensional spectrum. Because different wavelengths of light penetrate to different depths in an atmosphere that let them locate the feature vertically and infer the chemistry around it. The result overturned the assumption. Dark spots on Neptune are probably not holes in the cloud deck, which is what everybody had reasonably supposed, a gap you are seeing down through. They appear instead to be a darkening of the air particles themselves, in a layer below the main haze where ices and hazes mix. And right beside the dark spot they found something that had never been seen at all. A small bright cloud at the same atmospheric level, a completely new type of feature. Those findings were published in Nature Astronomy on the 24th of August, 2023. So 34 years after the flyby, the first proper measurement of what Neptune's most famous feature actually has arrived. And it was not what the flyby era interpretation said. That is one revision. Here are two more, and they are worse. The first concerns the clouds. In 2023, a study led by Irandy Chavez assembled 29 years of imaging of Neptune. Hubble observations going back to 1994, images from the Keck Observatory's near-infrared camera with adaptive optics from 2002 onward, and observations from Lick Observatory in 2018 and 2019. It was the longest continuous record of Neptune's appearance that has ever been assembled. What it showed is that Neptune's clouds have gone. The change began in late 2019 and had persisted through June of 2023. Apart from a residue near the South Pole, the cloud deck of the windiest planet in the solar system had substantially vanished. Not thinned gradually over decades, present in one set of images, effectively absent shortly afterward. And the correlation the team found is stranger than the disappearance. Across the 29-year record, they could count roughly 2.5 cycles of cloud activity, and those cycles track the Sun's 11-year activity cycle, with a lag of about 2 years. The proposed mechanism is that heightened solar ultraviolet during solar maximum drives photochemistry high in Neptune's atmosphere, and the products of that chemistry take a couple of years to percolate down into the layers where clouds form. Which means the weather on a planet receiving 1/900th of our sunlight answers to the Sun anyway, on a delay, through chemistry, 4.5 billion kilometers out. The second revision concerns the temperature, and it comes in two parts, both unexpected. In April of 2022, a team led from the University of Leicester published a 17-year thermal record of Neptune in the Planetary Science Journal, built from the European Southern Observatory's Very Large Telescope and a number of other ground-based and space-based facilities. Their first finding was that between 2003 and 2009, Neptune's stratosphere cooled by at least 7 degrees Celsius. That interval spans Neptune's southern summer solstice in 2005. Summer arrived, and the planet got colder. Their second finding was more dramatic. Beginning around 2018, Neptune's south polar stratosphere warmed by roughly 11 degrees Celsius in about 2 years. Rapid polar warming of that kind had never been observed on Neptune before. The paper lists candidate causes, changes in stratospheric chemistry, random weather variation, the solar cycle, and commits to none of them. Then, in March of 2025, came the one that reframes everything. A team led by Henrik Mellin published in Nature Astronomy the first detection of infrared aurorae at Neptune. They used the near-infrared spectrograph on the James Webb Space Telescope on data taken in June of 2023 as part of a guaranteed time solar system program. The spectrum showed a strong emission line from the trihydrogen cation, H3+, which is the standard auroral fingerprint at every giant planet. And the aurorae appeared where the 47-degree magnetic tilt says they should, at mid-latitudes, not at the poles. Mellin's own reaction to seeing it was that the detail and clarity of the signature shocked him. This had been the missing piece for decades. Aurorae had been confirmed at Jupiter, at Saturn, and at Uranus. Neptune was the one that would not give them up, and people had been trying with the best ground-based facilities available for years. Alongside the aurorae, the team did something else. They measured the temperature of the top of Neptune's atmosphere, the ionosphere, for the first time since Voyager 2. Here is what Mellin said about the result as quoted by NASA. "I was astonished. Neptune's upper atmosphere has cooled by several hundreds of degrees. In fact, the temperature in 2023 was just over half of that in 1989. Half. Not a refinement. Not a correction at the margins. The upper atmosphere of the planet is now at roughly half the temperature that has been sitting in the reference tables for 36 years. And then comes the part that I find genuinely unsettling, and it is the reason this section exists at all. That stale number is why nobody could find the aurorae. For decades, astronomers estimated how bright Neptune's aurora ought to be by using the temperature Voyager 2 measured. Predicted brightness depends strongly on temperature. A substantially colder ionosphere produces much fainter emission, so every search was calibrated against a value that had stopped being true, and every search therefore expected something brighter than what was there, and every search came back empty. Think about that mechanism for a second, because it is quietly vicious. The old number did not simply sit in a table being wrong, it actively defeated the observations that would have revealed it was wrong, and it did so invisibly. Nobody was making an error. Everybody was using the best available measurement. The best available measurement was 30 years old from one afternoon, and the planet had moved on without telling anyone. There is a further twist in it. The colder the ionosphere becomes, the fainter the H3+ emission, and the harder it is to detect the very signal that would tell you about the cooling. The effect conceals itself. Neptune got harder to read by getting colder, and getting colder is the thing you would want to read. And I want to be fair about the polar warming, because there is a detail that makes it harder to explain rather than easier. Neptune's seasons last more than 40 years, which means the South Pole had been in continuous summer for decades by 2018. If you wanted to attribute a warming to the arrival of summer, the timing is wrong. Summer had already been there a long time. Something changed in the middle of a season that had been running for a generation. There is also a structural problem behind all of these results, and it is worth naming plainly. Jupiter and Saturn receive continuous dedicated attention. There are monitoring programs, amateur networks contributing usable data nightly, decades of consistent coverage. Neptune has nothing of the kind. There is no ongoing dedicated Neptune monitoring campaign. Every one of the records I have just described, the 29-year cloud study, the 17-year thermal record, was assembled retrospectively, stitched together out of telescope time that had been granted for other purposes, by people who went back through archives and worked out what could be salvaged. Which puts the 17-year thermal record in an unflattering light when you convert the units. 17 years is about 1/10 of a Neptunian year. The longest continuous temperature record that exists for the 8th planet covers 1/10 of a single orbit. Imagine trying to characterize Earth's climate from 5 weeks of data, and then imagine that those 5 weeks were the only 5 weeks anyone would collect for the next century. Now let me ask you to hold 2 images at once, and hold them steadily, because this is the center of tonight. The first image is the one you already have. Deep blue, sharply banded, the great dark spot sitting like a bruise in the southern hemisphere, a crisp portrait of a planet. The second image is Neptune as it actually is tonight, paler than that and greener, effectively cloudless except near the South Pole. No great dark spot. It has been gone for about 30 years. An upper atmosphere at roughly half the temperature of that portrait. A polar stratosphere that warmed 11 degrees in 2 years for reasons unknown. Aurorae at the middle latitudes that nobody could see until 3 years ago. Now put the gap between those two images into the shape it really has. 37 years. In that time, Neptune has been through one full season change, one of its 40-year seasons ending and another beginning, entirely unwatched at close range. The most interesting weather event in the recorded history of the planet could have happened in 1997, or 2004, or last March. If it did, there is no record of it. There is no way to recover one. It happened at a place where nothing was watching, and it is gone, and the only trace it left is a number somewhere that does not quite match. You cannot go back and take that data. Time series measurements are the one thing in science that genuinely cannot be recovered later. You can rerun an experiment. You can rederive a calculation. You cannot go back to 1997 and look at Neptune. So the file we have on the 8th planet is not incomplete in the ordinary way, where more work will fill it in. It is missing 37 years that no future mission, however good, will ever be able to supply. And that is the point at which the obvious question becomes unavoidable. If the file is this bad, and the planet is this strange, and everybody involved knows it, why has nobody gone back? Let me step back and restack everything, because we have accumulated a great deal, and the shape of it matters more than any individual item. We have a planet that was found by arithmetic in 1846 and visited for a matter of hours in 1989. Its winds are the fastest in the solar system, above 2,000 kilometers per hour, and they cannot be powered by the sunlight arriving there, which is 1/900th of ours. It radiates 2.6 times more energy than it absorbs, and its near-identical twin next door radiates almost none, which means the difference between them is a fact about internal architecture that nobody has measured. Its magnetic field is tilted 47 degrees and centered more than half a planetary radius, away from the center of the planet, so its magnetosphere has no stable shape, and its aurora glow at the middle latitudes. It has no surface, no floor, no strata, and no direct in-place measurement of any kind. Its interior probably contains water in a state that is solid and liquid at once, and carbon precipitating out as diamond, and those two things together may be the answer to both the heat and the magnetism. It has a moon that arrived from the Kuiper belt, orbits backwards, is falling slowly inward toward destruction, erupts 8 kilometers into space at 38 Kelvin, has an atmosphere that is warming for unknown reasons, and has never been photographed across 60% of its surface. And since the one visit, the defining storm has vanished, the clouds have vanished, the stratosphere cooled through summer, the South Pole warmed 11 degrees in 2 years, and the upper atmosphere is now at half its recorded temperature, a discrepancy so consequential that it silently defeated 30 years of attempts to detect the planet's aurorae. That is the situation. And the obvious next question is the one everybody asks. Well, it is very far away. What did you expect? I want to take that objection seriously, because it is the wrong answer, and understanding why it is wrong is what makes the last part of this video land. Distance is not the problem. Distance is barely even a factor. Here is the honest accounting. Neptune sits at about 30 astronomical units from the Sun. Light takes roughly 4 hours to get there. That means a radio command sent from Earth arrives 4 hours after it leaves, and any reply arrives 4 hours after that. A minimum 8-hour turnaround on any conversation. That is a real operational constraint, and it is why the Voyager 2 encounter had to be fully pre-programmed, with no possibility of reacting to anything. But 8 hours is not an obstacle to a mission. It is an inconvenience that spacecraft engineers solved decades ago by making probes autonomous. The Mars rovers already operate on a similar principle at a fraction of the distance. Nobody has ever cancelled an outer planet's mission because of light delay. Voyager 2 took 12 years to get to Neptune. That number gets quoted as though it were a measure of how impossibly remote the planet is. It is not. It is a measure of what gravity assist can buy you. Voyager 2 got there in 12 years using a once-in-a-lifetime alignment of all 4 giant planets that let it slingshot from one to the next. And the real currency of spaceflight is not distance at all. It is velocity change, delta V, the total amount of speed a mission can add or subtract along the way. Getting somewhere is a matter of adjusting your orbit around the Sun until it intersects the orbit of your target at the right moment. Kilometers are almost incidental. What costs you is changing speed, and the exponential cruelty of the rocket equation means that every extra bit of speed demands disproportionately more propellant, which itself has to be accelerated. This is why a trip to Mercury can be harder than a trip to Mars despite Mercury being closer. It is why the Messenger mission needed 6 planetary flybys and nearly 7 years to reach a planet that is a short hop away in raw distance. The map that matters is not a map of distances, it is a map of speeds. For Neptune, the delta V accounting comes out like this. Reaching the planet with a gravity assist from Jupiter takes something like 12 years. Reaching it without one, going direct on the strength of the launch vehicle alone, takes about 16. 4 years of difference. That sounds like a scheduling detail. It is not. It is the difference between a mission whose principal investigators see their own data and a mission whose principal investigators do not. It is 4 more years of a spacecraft's radioisotope power supply decaying before arrival. It is 4 more years of budget, 4 more years of a team held together, 4 more years of institutional memory that has to survive, and getting the assist requires Jupiter to be in the right place. That is the actual constraint, not distance, not technology, not physics, geometry, and its schedule. It is worth dwelling on how much a gravity assist actually gives you, because the mechanism is one of the most elegant things in orbital mechanics, and it is easy to mistake for a trick. A spacecraft flying past a planet steals momentum from it. Not much, on the planet's terms. Jupiter is so massive that the effect on its orbit is unmeasurable. But on the spacecraft's terms, it is transformative. You approach the planet, its gravity swings you around, and because the planet itself is moving, you leave with a different speed relative to the Sun than you arrived with. Energy is conserved. It has simply been transferred from a body with the mass of Jupiter to a body with the mass of a small van. This is not optional for the outer solar system. It is the only way anything has ever got there. Voyager, Galileo, Cassini, New Horizons, Juno. Every one of them borrowed from a planet. And the price of borrowing is that you have to be at the lender's address when the lender is home. There is a second constraint stacked on top, and it is the light. Remember the phrase we started with. High noon on Neptune would look like dim twilight to us, 900 times fainter than the daylight you know. That was an atmospheric image when I first said it. Now it becomes hardware. Solar panels do not work out there. Not work poorly. For a flagship-class spacecraft with real instruments, they are simply not an option at 30 astronomical units. Juno manages it at Jupiter with about 60 square meters of array producing a few hundred watts, and Jupiter receives roughly 25 times more sunlight than Neptune does. Scale that down and you get a power budget that cannot run a mission. So a Neptune orbiter has to carry its own energy source, which in practice means radioisotope power. Plutonium-238, decaying, producing heat that is converted to electricity. That is proven technology. It is what Voyager runs on, and what New Horizons runs on, and what Curiosity and Perseverance run on. But plutonium-238 is not something you buy. It has to be manufactured, deliberately, in small quantities, in specialized facilities, and the global supply is genuinely limited. The amount of it available is one of the real factors that determines how many outer solar system missions can exist in a given decade. And there is a third constraint, which is arrival. Flying past Neptune is one thing. Voyager 2 did that at more than 16 kilometers per second and simply kept going. Going into orbit means shedding an enormous amount of velocity, and you cannot do that for free. You either carry the propellant to brake, which is expensive in the exponential way, or you attempt something clever, like aerocapture, using a pass through the planet's upper atmosphere to slow down. Aerocapture appears in mission studies for exactly this reason, and it has never been performed at any planet. Ever. So, an 8-hour conversation delay that is manageable, a 12-year cruise that requires a planetary alignment, a power supply that has to be manufactured atom by atom because the sun is too dim to help, and an arrival maneuver that either costs a great deal of mass or uses a technique nobody has ever demonstrated. And I should be clear that we know this list is surmountable because the analogous list was surmounted twice already. Getting an orbiter into the Jupiter system and keeping it alive in the worst radiation environment in the solar system was harder than anything on the Neptune list, and Galileo and Juno both did it. Getting a spacecraft into orbit at Saturn, dropping a lander through the atmosphere of Titan, and then flying 22 orbits between a planet and its rings before deliberately destroying the spacecraft to protect a moon. Cassini did all of that, having launched in 1997 with computers less capable than the device you're probably holding. None of that is impossible. All of it is engineering, and it has all been studied in detail, and there are worked-out mission designs sitting in journals right now describing precisely how to do it. There is only one thing missing, and it is the thing this whole video has been walking toward. Somebody has to launch before the geometry closes, not somebody eventually, not somebody when the technology is ready, because the technology is ready. Somebody now, in the sense that the decision has to already have been made, the money already committed, the hardware already being welded together in a clean room, because a flagship mission takes the better part of a decade to build after it is approved, and the geometry has a date on it. The favourable alignment for sending a spacecraft to Neptune with a gravity assist from Jupiter runs from 2029 to 2030. That is the sentence. Everything else in this part is elaboration on it. Here is how the arithmetic works out in the published studies. A mission designed against that alignment would launch around 2031 on a heavy-lift vehicle, take the Jupiter assist on the way out, and arrive at Neptune around 2043 after a 12-year cruise. Launch after that and the Jupiter option is gone. The planets are no longer arranged to help, and a direct trajectory stretches the cruise to about 16 years. The alignment recurs on roughly a 12-year cadence, because that is approximately how long Jupiter takes to go around the Sun and line up again with Earth and the outer planets. So the question is never whether Neptune can be reached. It is whether a spacecraft is built and sitting on a pad while the window is open. The window is open now. Let me tell you what exists on paper, because a great deal does, and it is good work. The most developed concept is called Neptune Odyssey. It is a flagship-class mission, the largest category, the Cassini category, consisting of an orbiter and a separate atmospheric entry probe. Its design is elegant in a way that reflects everything we have discussed. It would orbit Neptune retrograde, which is to say prograde with respect to Triton, so that Triton's own gravity could be used repeatedly to reshape the orbit and steer the spacecraft around the system. The captured moon becomes the tool for exploring the planet that captured it. The concept was worked up in detail and published in the Planetary Science Journal. Its reference profile launches in 2033, cruises for 16 years, arrives in 2049, and conducts a 4-year primary mission. Sit with those numbers for a moment before I tell you what happened to it. 2049 for arrival, then a 4-year primary mission, so the substantial science is coming in through the early 2050s. Then the years it takes to reduce the data, publish it, argue about it, and revise the models. Call it the mid-2050s before we genuinely understand the interior of Neptune. A person who is 50 years old today would be in their 70s before the first orbital measurement of Neptune's gravity field existed, and pushing 90 before the mission wrapped up. A person who is 70 today will not see it. A child born tonight would be in their late 20s when the spacecraft arrived, which is in fairness a rather beautiful thought, and it is the version of this that scientists hold on to. Now, here is what happened to Neptune Odyssey. The Planetary Science Decadal Survey is the process by which the American planetary science community, roughly every 10 years, sets its own priorities, a document assembled by hundreds of scientists that effectively determines what gets built. The survey covering 2023 to 2032 did consider Neptune Odyssey seriously. It did not recommend it. For reasons of cost and logistics, including launch vehicle availability and the specific launch windows available, the survey made a different ice giant mission its highest priority flagship, the Uranus orbiter and probe. That mission was ranked ahead of even an Enceladus mission, which tells you how strongly the community feels that an ice giant orbiter is the missing piece of solar system science. Neptune Odyssey was named a high priority concept for a subsequent round of ice giant exploration. I want to be careful and fair here, because this was not a foolish decision. It was, on the merits, defensible. Uranus is closer. Uranus has its own favourable Jupiter window in the early 2030s. Uranus's 98-degree tilt and its missing internal heat are first-rate scientific problems, and most importantly, a single ice giant orbiter, either one, would transform our understanding of the most common class of planet in the galaxy. The community looked at 2 badly understudied planets, could realistically fund one, and chose the nearer one. But the consequence for Neptune is simple. High priority concept for a subsequent round means later, and later, for Neptune, has a 12-year clock attached to it, plus a 12 to 16-year cruise on top of that. There is a further irony in the Uranus decision that is worth noting, because it shows how tightly all of this is bound to geometry rather than to will. The Uranus orbiter and probe was itself partly prioritized because of a Jupiter window, a favourable alignment in the early 2030s that would let it reach Uranus reasonably quickly. Windows are why Uranus won. Windows are also why Neptune is losing. The same physics that made one mission urgent made the other deferrable, and nobody in the process was being careless. And there is a hard constraint underneath the whole discussion that has nothing to do with priorities: the plutonium. A flagship orbiter at Neptune needs a substantial radioisotope power supply. That material is produced in tiny quantities by a small number of facilities, and the available inventory in any given decade limits how many deep space missions can fly at all. When a community chooses one ice giant, part of what it is choosing is where the fuel goes. The Triton mission fared the same way. A Discovery-class flyby called Trident was proposed, aimed at the 2030s, designed to determine whether Triton has a subsurface ocean and to photograph the hemisphere no one has ever seen. It was not selected either, so the position, as of tonight, is this. There is no approved mission to Neptune. There is no spacecraft being built. The Jupiter window closes around 2030, and the only machine that has ever measured the planet is losing a few watts of power every year, having its instruments switched off one at a time, with an expected end sometime in the early 2030s, which produces a genuinely strange piece of scheduling. Voyager 2, the sole witness, the source of nearly every number we have about the eighth planet, will most likely fall silent before any replacement has launched. Not before it arrives, before it leaves. And there is a quieter cost to that timing which is easy to overlook. Institutional knowledge does not survive gaps well. The people who designed the Voyager encounters, who worked out image motion compensation in flight, who knew from experience how an ice giant flyby behaves, most of them have retired, and many have died. The engineers who would fly a Neptune orbiter in the 2040s will be learning outer-planet operations from documents, rather than from the people who wrote them. Every decade of delay does not just postpone the data, it thins out the expertise that would collect it. Let me put you in the mission that does not exist because it is worth seeing what we are not doing. It is the early 2030s. A vehicle lifts off carrying an orbiter and a probe, and a supply of plutonium that was manufactured gram by gram specifically for this. It swings past Jupiter and steals a fraction of that planet's momentum. Then it goes quiet, and it stays quiet for 12 years, coasting outward through the region where there is nothing at all. Past the asteroids, past the orbit of Saturn, past Uranus, the sun shrinking behind it until it is the brightest star in the sky and nothing more. It arrives in the 2040s, into light 900 times fainter than the light in your window. It breaks, hard, and settles into a long looping orbit shaped by a captured moon, and then it drops the probe. The probe falls into the clouds we described earlier, through the methane cirrus, into the thickening dark, transmitting continuously. Pressure climbs, temperature climbs. It reports composition, ratios, temperatures, the things nobody has ever measured in place at this planet, and it does this for perhaps an hour before the atmosphere destroys it. That hour is the entire in situ chemical record of the eighth planet, for all of history to that point and for a long time afterward. Now step out of that and hold on to this. It is not happening. No such spacecraft is being built. No such launch is funded. The alignment that makes the 12-year version of that journey possible ends around 2030, and after that the same trip costs 4 more years and has to wait for Jupiter to come round again. And I do not want to leave the impression that this is only one nation's decision to make. The window belongs to whoever uses it. There are proposals elsewhere. China has studied outer solar system concepts that include an ice giant element, and it is entirely possible that the eighth planet gets visited by somebody who has not visited it before. That would be a fine outcome, but no such mission is confirmed to be launching into this window either. So we arrive at the position I have been walking you toward for 2 hours. We know Neptune is one of the strangest objects in the solar system. We know our information about it is 37 years old, came from one afternoon, and has been demonstrated to be wrong in at least 3 specific and significant ways. We know exactly what to build to fix that, and we have written the mission designs, and we know the specific years in which the journey is cheapest. And we are right now letting those years pass. I want to be honest that this is not a scandal, and nobody is at fault. Every individual decision in the chain was reasonable. The choice to send Voyager 1 to Titan was correct. The choice to bend Voyager 2's Neptune flyby toward Triton was correct. The choice to prioritize Uranus was defensible on the merits. There is no villain here, and no conspiracy, and no suppression. That is precisely what makes it worth sitting with. This is what it looks like when a whole planet slips out of view through a series of sensible choices, each of which was the right call at the time, which finally lets me answer the question I posed at the very beginning. Neptune is the scariest planet we will never reach, and it is not because of the winds. It would be easy to end this the obvious way. 2,000 kilometers per hour, minus 200 degrees, no ground, diamonds falling in the dark, pressure that would flatten anything we could build, a moon spiraling toward its own destruction, a magnetic field so lopsided that the concept of north dissolves. That is a frightening inventory, and every item on it is true, and if you wanted to make a case for Neptune as the most hostile world in the solar system, the case is right there. But none of it can frighten you, and I said so at the start. Nobody is going. There is no plan to put a human being anywhere near the 8th planet, in your lifetime or your grandchildren's. A place that cannot be visited cannot be dangerous. The winds are not a threat, they are a fact about somewhere else. So here is the answer. What is frightening about Neptune is that it is the only planet in the solar system whose file is closed. Everything we say about it, confidently, in textbooks, on posters, in documentaries, in the little paragraph that comes up when you search for it, traces back to 12 hours. One afternoon, in 1989, by one aging spacecraft moving at 16 kilometers per second, in light 900 times too dim, taking photographs it had to be reprogrammed in flight to compress, whispering the results back across 4 hours of empty space to an array of antennas on 3 continents straining to hear it. That was magnificent. It remains one of the great single days in the history of exploration, and I want to be exact about what I am saying because it is not a criticism of that day. The problem is not that the measurements were poor. The measurements were superb. The problem is that a single measurement cannot argue with itself. Remember how Neptune was found. Leverrier noticed that a number about Uranus was slightly wrong, and refused to let it go, and followed the wrongness all the way out to a new planet. That is the engine of science. You measure something repeatedly, and discrepancies surface, and the discrepancies are where the truth is hiding. That engine requires repetition, and Neptune has been measured up close exactly once. So its numbers sit in the reference tables not because they have been confirmed, but because nothing has ever been in a position to contradict them. And then, over the last few years, things finally got into position. Telescopes good enough to make a few of those measurements from 4.5 billion kilometers away. And look at what they found the moment they were able to check. The great dark spot is gone, and has been for about 30 years, and nobody watched it go. The dark spots are not holes in the cloud deck at all, which is what the flyby era interpretation assumed. They are darkened particles below the haze, and they come with bright companion clouds that nobody knew existed. The clouds themselves have all but vanished since late 2019, and their comings and goings answer to the sun's 11-year cycle on a 2-year delay. The stratosphere cooled by 7 degrees through the arrival of summer. The South Pole warmed 11 degrees in 2 years, in the middle of a season that had already been running for decades, for reasons nobody can name, and the top of the atmosphere is now at just over half the temperature Voyager 2 recorded. Half. There it is. That is the whole thing, in one number. And the detail I keep returning to, the one I find genuinely unsettling in a way the winds never could be, is what that stale number was doing while it sat there being wrong. It was not inert. For 3 decades, astronomers used it to predict how bright Neptune's aurorae should be, and because they were working from a temperature that was far too high, they kept expecting something brighter than what was there, and they kept finding nothing. The old measurement was quietly defeating the observations that would have exposed it. Nobody made a mistake. Everybody used the best available data. The best available data was the problem. That is a kind of failure we do not have a good name for, and we do not have a category for it either. We are comfortable with not knowing. Not knowing is respectable. It is what the far side of the Kuiper belt is, what the interior of a black hole is, what dark energy is. Those things sit in a mental drawer labelled open questions, and we are at peace with them, and there is even a pleasure in it. Neptune is not in that drawer. Neptune is in the drawer labelled known. It has a full entry: diameter, mass, wind speed, temperature, magnetic tilt, moon count, ring names. Nothing about that entry announces itself as provisional. A child copying it into an exercise book has no way of telling that they are transcribing a document from 1989, from one pass, several of whose lines have since been shown to be wrong, and it is worth noticing how much of that entry is not merely old but structurally unverifiable from here. The interior model, the supersonic water, the stratified layers, the diamonds precipitating out and releasing heat as they sink, is a chain of reasoning anchored at one end in laboratory experiments on Earth, and at the other end in a magnetic field measurement taken in a few hours in 1989. It is a good chain, it may well be right. But no telescope can weigh the inside of a planet. That requires an orbiter, tracked precisely as the planet's uneven gravity tugs at it, over many passes. When Juno did that at Jupiter, it found the core to be diluted and fuzzy rather than sharply bounded, which nobody had predicted from flyby data. When Cassini did it at Saturn, it settled questions that had stood for decades. Flyby data told us one story about Jupiter's field, and orbital data told us another. Neptune has only ever been seen from a flyby. A planet is not a photograph. I said that earlier, when the great dark spot turned out to be temporary, and it was a small observation about one storm. Let me give it its full weight now. What we have of Neptune is a photograph, not a metaphorical one, a literal set of images and instrument readings from a single afternoon, and we have been treating that photograph as a planet, as a description of an ongoing object rather than a record of one moment in the life of one. The picture has been standing in for the thing, and the thing has been out there the whole time, changing, moving through a 40-year season nobody watched, with a storm the size of Earth dissolving in it unobserved. 37 years, one complete season change, and time series data is the one thing in all of science that cannot be recovered later. You can repeat an experiment, you can recompute a result, you cannot go back to 1997 and look at Neptune. Whatever happened there in the intervening decades has already gone, permanently, and no mission, however brilliant, will ever be able to supply it. So the gap in our knowledge of the eighth planet is not the ordinary kind that patience fills in. Part of it is closed forever, and the correction for the rest of it, the part that could still be fixed, has a date on it. The Jupiter alignment that makes the journey cheapest runs from 2029 to 2030. Nothing is funded to use it. The best worked out mission, Neptune Odyssey, would arrive in 2049 and finish in the early 2050s. For a great many people listening tonight, the first real measurement of the inside of Neptune is scheduled for after they are dead. And that is the optimistic version, the one where the mission gets approved. Meanwhile, Voyager 2 is still out there, still transmitting, still the only machine that has ever been close to the planet, its instruments being turned off one by one to conserve a power supply that fades by a few watts a year, expected to fall silent sometime in the early 2030s. The only witness is dying, and no one has been sent to take a second statement. And there is one more reason this is not a parochial concern about one distant world. When astronomers survey planets around other stars, the most abundant category they find is not Earth-like and not Jupiter-like. It is a world in this exact size range, a few times Earth's radius between rocky and gas giant. The commonest kind of planet in the galaxy, as far as anyone can currently tell, is Neptune-like. We have two local examples. They contradict each other about how a planet retains heat, and neither has ever been orbited. So every time a telescope finds one of those worlds around another star, and we estimate its composition, its interior, its likely history, we are doing that estimate using a template, and the template is Neptune from that afternoon. That is the fear. Not the cold, not the pressure, not the wind that moves faster than sound in an atmosphere 900 times too dark to see it. The fear is a small, specific domestic thing. It is the discovery that we know is sometimes a sentence about the past, that a fact can sit in a book for 37 years, be repeated by every source, be taught to millions of children, and describe an object that no longer exists in that form. And there is nothing wrong with the planet. I want to end on that, because it matters. Neptune is not menacing anybody. It is out there doing exactly what it has done for 4.5 billion years, turning every 16 hours, leaking heat from somewhere inside itself, driving its supersonic weather in the dark, letting diamonds fall through an ocean that cannot boil, holding a captured moon that erupts on the coldest ground we have ever measured and is slowly falling toward being torn into rings. It is entirely indifferent to whether we look. The unsettling part belongs completely to us. It is in the gap between how confidently a thing can be described and how little of it has actually been checked, and in the recognition that this gap is not unique to Neptune. It is just unusually easy to measure there, because there is exactly one visit to count. So the next time you see the 8th planet at the end of the diagram, the last one, the blue one, the windy one, try holding it slightly differently. Not as the final entry in a completed list, as the one place in the solar system where we know precisely how old our knowledge is and how much has changed since, and exactly which years we are letting slip past. Neptune is the scariest planet we will never reach, not because of what is there, because of how sure we sound about it.